Mike at MULTIAXIS with this e-learning focused on creating your first project. It's going to be divided up by single path, two path, and three path style controls for the turret series from Nakamura. To start off, you're going to navigate to your e-learning and to the Complete Turn Mill Introductory and the version you're running. For this e-course, we're going to download the part geometry and resources. In a previous e-course, we already downloaded the generic tooling blocks and work holding. If you haven't already downloaded this and imported it into your resource manager, you can go ahead and download these two now. We're going to start off by downloading the part file. And extract this to our training file folder for turn mill. In this folder are two files. They are WRL format. There's one for the main and sub. Depending on the single path, two path, or three path, you might use both models or you might use just one. Can navigate back to the support site, and now we're ready to begin this e-course focused on single path, two path, or three path style controls. This first part of this e-learning lesson will focus around using the software with the single path control. You can navigate to the introductory e-learning, and at the top right under the part geometry and resources you'll find the different series broken down. The SC and the AS series are a single path control. We're going to go right to the AS series and download the two zip files and extract them to our training file folder once they're done. So in my turn mill folder, I'll extract this. Let's review the two files that we've downloaded. Start by opening the PDF file. This contains two pages, one for a 3D reference showing us the machine overlay with no guard work on, path 1, main and sub spindle with the codes associated with it. A standard program format that shows us how to start our program, how to begin, how to start a new path, how to call a tool, how to end a tool path, and how to end our program. And these can be used as a reference when creating your G-code programs. In the AS Series 200 folder, you'll find program 01001 P-1. Having the P-1 extension will automatically load it in path 1. This program contains only one tool working on the main spindle. And one thing to note when we work in the project is how we call the tool. We can automatically assign the tooling block using this format. Let's begin. Go ahead and open Turn Mill from the top ribbon bar. Make sure we select Project and select your machine. We'll select our AS200 and we can set it as the default if you want, if that's your plan to use that machine moving forward. Document units are very important. This first project is in millimeters, so make sure we select millimeters. And say select, and once the machine's loaded, we'll begin adding our resources. For this project, we're just going to work on the main spindle, so let's load some work holding under the project ribbon bar, main. This brings up our work holding dialog. We can choose main or sub. It's just like going back up here and going to sub, just quickly goes right to sub. We'll select main, and it defaults to the chuck column first, and we have part and stock. Under chuck, we'll say select, and once this pops up, we'll start our filtering just by looking at available chucks that fit on this machine. So it looks like I have an 8-inch 2-jaw and 3-jaw. We could say the 8-inch 3-jaw, okay. And I can see it start to build the setup in here. choose my chuck options. This is automatically filtering here. Say chuck number jaw 4 here. And we'll bring in our part by going to part here. We can set a part stick out length, so I'm going to have it stick out from the main spindle 80 millimeters, and I'll import the geometry. Go in our training file folder under the turn mill part file metric. We can choose our file handler on the the right hand side here. We can bring in IGES, STL, VRML files, or CSI geometry from Complete. This file is a VRML file, so we're going to select the VRML file .WRL format. We'll open up the part file. We can say main spindle, and this was in millimeters, so we'll just say OK. We'll close this, and we can zoom into the setup, and we can see it's currently set up on the main spindle. We're not working on the sub spindle, but since we're working on this machine, we will load a chuck on the sub spindle. Say select, we'll filter, and this fits our 6-inch chucks here. Choose our jaw configuration. Looks like I got a couple different jaws that can work here. Say OK, and I can load a part. And this will go back to the last directory you were working in and use the last file handler. We'll select the sample 1 sub and say open in millimeters. And this time I didn't set a value first, so I could import the geometry and then set it after. And this is in machine coordinates, so you would say a minus when working on the sub spindle. We can bring our tool holder in. I'm going to navigate through my next view here so I can see it without the guard work. Go to my top ribbon bar project, tools. This brings up my tool table, and on station number 1 I can select the plus symbol. I can filter the available tool holders that can work on this turret. Go to my turning tool and say OK, and you can see it start building the turret setup. I can select my library selection here, and it filters through available cutting tools that fit on that. Now before we leave this page, we can change the extension length fairly easy on this, just by clicking this little adjust extension box here, and we can manually jog it. We can auto adjust by machine position, so if you were a boring bar inside the machine, you could just move the machine around it. Or you can specify a stick out length here, 60.0 millimeters, or you could say even inch value here if you wanted to, and it will automatically convert it. On the tooling page, if you were working on the sub spindle, the default on this machine is facing the main. You would just hit flip, and the TLO reference would reference the sub spindle now. So these offset values are in reference to that work holding and part. When I flip it the other way, it's in reference to this work holding and part. Close this. Now that my resources are in, I can bring in my program just by going up to the program ribbon bar, import G-code. In our training files, we have the AS series folder, program 01001 P-1, and say open. I can regenerate this just by selecting the program up top here. Now I could have multiple instances of this in here, and I'll show you just by re-importing that program again. And what you can see is we have 2 instances of the same program. I could be working in one, and I could be making edits in another. You can only have one active. This is like memory mode at a time, and whichever one has the red flag will be the one that creates the generated interpolated motion here. If you need to delete a program, you can just highlight the program and press delete on your keyboard. Once you have an active program up top here, you choose your path you want to generate, and at the bottom here, press start. It will go through the program, check for any ambiguous errors, and report back if there's an error during regeneration. This is complete, and it's ready to simulate. while it's simulating, you can move around and zoom in and watch the simulation. Once this is done, you can export the G-code. Choose a directory. Just going to use the TurnMill directory and say select folder. It sees if there's any file that already exists. You can say Open File Explorer after and say export. There's our program. So we started with a program, we can export a program, we might make modifications to it, and we'll review that a little bit later on in our e-learning lessons. Now for this example, you could flip this to work on the subspindle. I do have the identical shape on the main and the subspindle here. All you have to do is go to the operation here, right click it and say Edit Operation. This brings up our operation properties editor. It allows us to mirror axes, remove axes, shows us the tool that is being used in the tool table, shows us a preview of the code that is for this path down below. We could actually make edits in here at this point. It's showing any type of G-codes that are being used in this program. We can just cursor through it and you can see it snaps right through those points. If I wanted to have this work on the subspindle, all I would have to do here is just click the subspindle and it will flip the tool and it will change the spindle codes from main to subspindle. We can mirror the z-axis, so now it's working in the machine axis in the opposite direction, and we can reverse any arcs that are being used on that path and just say OK. And it wants to know if you want to apply the update. You can say yes. Anytime we make any type of changes to the program, it requires us to regenerate the interpolated motion, so we have to go back to regenerate, reset it, and start. And if there are any ambiguous errors, it will stop and it will show you. We can press simulate and play. And now this project is working for the subspindle. Going to move this operation back to the main spindle just by right-clicking it, saying Edit Operation. I can go back to main, mirror the Z and reverse the arcs. Say OK, yes. Now before I regenerate this program, I just want to show you a little bit about how this project navigator is selecting this operation. So I'm going to go ahead and actually remove this tool holder just by selecting it and deleting it and saying close. And I'm going to go to the program here and select it, and I can press edit under the program ribbon bar. I can use this little edit pin here next to the program. This launches our G-code editor, and as we navigate through the program here, it actually jumps right to those sections. So in TurnMill, it thinks this is the start of the program, this is the beginning of an operation, and this is the end of the program. So if we were to right click any of these operations and say Edit Operation, it will only show you the properties for that section. So you can see here when I right click that %, it's only showing me the beginning of the program. If I right click the M30 and go Edit Operation, it's only showing me the end of the program. So how is this happening? So if I select this, the way TurnMill looks at the operations is it looks for a line number, an M code, and a comment to issue the start of an operation. So if you do this in Camply TurnMill, it's going to list it in this program navigator tree here by your operations. So you could drag and drop these operations around and reorder them in the program. Now the next feature I'm going to show you is how you can automatically assign this tooling block for this. So on the tool change by itself, if you have a comment that matches the name in your resource manager. So on the resource manager, I have a block called generic tool block turn 80mm. If it finds it, it will automatically assign it. So all you have to do in the program is just highlight the program number, and up the top under the program ribbon bar, press the Assign Tools. When you press the Assign Tools, the tool table shows up and it shows you the tool call in the program, and it sees that there's one section here where it wants to load it, and this is the station on number 1. If we press Auto Select, it will automatically select that tool holder and load it in the turret. So if you had a program with a lot of different tools, this can save you a lot of time when populating the turret. Now, this is not the tool offset page, but on the same page you can select your database and the cutting tool for this tool holder and say close. So a couple different ways to manipulate the data in your project. Now, anytime you enter the program editor, just by selecting the program and pressing your edit pin or edit under the program ribbon bar, you can navigate in this G-code and hand type in any G-code you want. You just got to remember you need to regenerate your interpolated motion afterwards. So as I start typing in it, you can see that it starts to check to see if the code actually works in the path. So it sees it, anytime you see the italicized information, it knows that it's not information that works in the machine. If I keep it in a comment and I press the edit pin, it saves these changes to the program and looks for a regeneration here. Now, even if you had a regeneration created and you wanted to redo it, you can just by pressing reset and start. Another item that requires the regeneration is if you make any type of tool offset adjustment. So if you find through simulation, I'm just going to use the navigator here by dragging it over here, that I want to be a lot shorter with the tool. So I'm going to zoom in here and go to my tooling page, and if I had a big enough screen I could see all this at once. I can go to that tool here and adjust the stick out length. I can just turn on this auto machine adjustment mode here so that the tool stays where it is and the machine moves around it. I'm going to say that I want this extension length to stick out just 30 millimeters, or maybe a little bit more, 35 millimeters, and say close. Say close here. Now anytime you make an offset change here, you'll see that it maintains the old offset information. So we need to force a regeneration just by going to Generate, Reset, Start. And now the interpolated motion takes into account the new offset for that tool. One thing you want to pay attention to is your simulation status in the bottom right hand corner. This is your visual indication if you have something not set correctly. The goal is to have all green. Right now, if I were to click in here, it is showing me that my collision checking is off. Now, one thing to pay attention to as well, if you were changing your feed rate overrides before you generate, I'll just turn this down, G0 and the G1 up, and create my interpolated motion. When I go back to simulate here, it's creating yellow on those overrides, and when I click it, it will show you the override settings that you have. So in order to get a green on this override, this has to be at 100%. The last item we need to do is turn on our collision checking so we get all green here. Go back to our Generate, reset the interpolated motion, and turn on collision checking. Check collision. Press Start and turn mill. When it's turning, it will create a swept surface around the outside shape, and that will be used as a collision checking entity. Once we're done with the collision checking, if it completes and there are no collisions, you'll have a complete green status here. When you press play, you will see the collision checking object here, which is the chuck spinning that you see in the 3D graphics window. The second part of this e-learning course will focus on two-path control on our turret series. If we navigate to our e-learning introductory turn mill, we can scroll down to our program and reference chart by series. The first two, SC and AS, we just reviewed, which were our single path control turret series, and the next two will be our two path control series, which are the WT and the WY series. So we're going to work in this example using the WT series just by downloading the two zip files, program reference, and our programs, and we'll extract these into our training file folder. And we will review these. In the WT series training folder, you will find two programs, one with a .p-1 extension and the other with a .p-2 extension. Now, having these extensions will automatically associate them to the correct path when you load them into TurnMill. These are not necessary, but they make you more efficient when importing data. If we were to look in each program, they're a single tool path using one tool. The upper is using tool number 1 and just turning. And the lower is using a single tool, turning, and tool number 2. The upper is working on the main spindle and the lower is working on the sub spindle. Now, if you're new to these series machines, the next file will help you guide you in a 3D overview of the common codes to look for in your program. So in this 3D diagram, you can see the upper path is path 1, the lower path being path 2, the main spindle turning and milling codes, and the coordinate system we use by default on the main, the coordinate system for the sub spindle we use by default, and the spindle turning and milling codes. By default, you'll see in this series that the upper tool will face the main spindle and the lower will face the sub spindle, and this is by design only. You can completely control which tool is working on the main and which tool is working on the sub. Next, on the second page is a standard program format for the upper path 1 and the lower path 2. They are broken down by start of the program, how to call up your tool, how to end your tool, and how to begin the next operation, how to end the program. So let's begin the project. So just like the way we started the project with the single path control, we always start by selecting the machine on the top ribbon bar using Project Select. We'll choose our WT series. Keep in mind, when you select something, it will highlight it in blue. The left-hand box selects the default machine. So if your plan is to always use that machine and you have more than one machine in this, the default machine is wherever you have this checkbox. Down the bottom here is very important of the document units. This project we're working with is in millimeters. Keep in mind, when you set this, you cannot change this after you set up the machine. You need to start over. Select this and load the machine. Now that we have the machine loaded, we can begin setting it up by navigating to our top ribbon bar project and to main or sub. We're going to load work holding on both. The default is to the chuck when you go to this page. We also have a choice for part and stock. We'll make sure we're on chuck and say select. We'll turn on our filtering, which will show us only the work holding that can fit on this spindle. We'll choose the 6-inch 3-jaw and say OK. Next, we'll choose some chuck options just by pressing select, and this automatically turns on the filtering. We could shut this off and override the setting, but by default it shows you the components that fit onto this chuck. We'll choose the sample 1 jaw and say OK. Next, we can load a part, since we're already on this main spindle program page here. We can set the stick out length just by typing a value in here. This is in machine coordinates. This will be 80 millimeters. And on the geometry, we'll say import, and this allows us to bring in IGES files, STL, Complete Solutions Geometry, or our VRML file, WRL. So we'll select our .WRL format and navigate to our desktop, to our training file folder. And in turn mill, we'll find our part geometry. We have both a main and sub spindle. WRL, we'll choose the main and say open. This wants to know the units it was created in. It is in millimeters. We'll say okay. And you can see it's starting to set up the machine inside. Next, we'll load the work holding and part on the sub spindle just by going back here and choosing sub. We'll select our chuck and we'll turn on our filtering. We'll choose the 6-inch 3-jaw and say OK. And you can see it starts building the setup. And we'll choose our component and choose sample 1 jaw. Next we'll load our part, and once again this is in machine coordinates, so we're going to say minus 80 millimeters and import our geometry for the sub spindle. Now it remembers the last folder you were in and the last file format you used when importing geometry, so keep that in mind. Open, and this was created in millimeters, and close. In the 3D graphics window I'm just going to change my view so I can see the actual setup here. And you can see that we have now the main and sub spindle work holding and part loaded. Next we'll be loading our tool. Now on the upper path we're going to load a block on station 1 facing the main spindle. On the lower path we're going to load a tool on station 2 facing the sub spindle. This brings us up to our project tools page, and if you have the lower minimized you can press this little blue tab here and that will minimize or maximize the paths. So I'm going to make sure I see both paths here, and on station 1, tool number 1, I'm going to press the plus symbol. Turn on our filtering and it will filter the blocks that will fit onto this turret. I'll choose the generic tool block turn 80 millimeter and say OK. Next you can see that it's building the upper tool turret assembly. We can choose our cutting tool, and when you select this it will only show us the tools that fit onto this block because the filtering is automatically turned on, and we'll say OK. While you're here you can set the stick out length of the tool just by selecting this little adjust tool length. You can manually adjust the stick out length here, or you can turn on the adjust machine position. If this was a boring bar and you were inside the part, you may want to set the stick out length using this. Or you can specify an extension length here. I'm going to choose 35 millimeters. Say close. Next on the bottom we'll select station number 2, tool 2, and press the plus symbol. Turn on our filtering and load in the generic turning block and say OK. Just like the upper path, we can select our cutting tool just by select from library. Automatically turns on the filters and shows us the stick tools that fit into that block. Say OK. And if you had a big enough screen or multiple monitors, you would see it building the setup as you add the resources. And just like the upper, we can adjust the stick out length manually or specifying a stick out length here. I'm going to say this is sticking out 2 inches. Just got to remember to specify the units. If the document units are in millimeters, the values you type in are in those units. But if you want to change the units, just type in the space or the IN after the number, and it will automatically convert it. Next, the upper tool should be facing the main. We do have full control over this. On the upper table here, we have to the right hand side a TLO reference datum, and this is telling us the tool offset is referenced to the main spindle. If we press flip, you'll notice it will flip it on the turret, and now our offsets are referencing the sub spindle. For this upper tool 1, we're going to face the main spindle, and for the lower tool we're going to face the sub spindle. Just like the upper, if we flip it, the offset references the main. Now we're ready to begin creating the interpolated motion for the programs we loaded. Now before we do this, we can choose whether to generate the path number 1 or the path number 2, or a combination of both. So think of this as upper memory mode, lower memory mode, or multi-memory mode. And this is in the middle here where it says regeneration required. So we select the path that we want to generate. I'll select the upper. And on the bottom simulation, under generate, we'll press start. When you have a full blue ribbon bar, you're ready to begin simulation. Just by going to simulate, our simulation controls are here and also up here. We can also use this little slide navigator by dragging it, and it moves like a video player anywhere in time in the generation. Now, if you wanted to change which path you were generating the interpolated motion for, you just select the lower or switch it here and shut off the opposite channel, generate, and we'll have to reset the interpolation so this blue ribbon bar will go completely white again, and we press start. And now the generated motion is based on just the lower program that you have selected here. While it's simulating, you can select your simulation subspindle and the orbit becomes focused around that subspindle. Now if you want to generate both paths at the same time, just simply turn them on and press generate, reset the interpolation motion and press start. Now both paths that you have selected in this trees, when you press simulate, work at the same time. You can focus your simulation around the main spindle or the subspindle for real-time simulation. Next, let's talk about the program navigator. You see this on the left-hand side for both the upper and lower path. You have a minimize or a maximize button by pressing the blue ribbon bar. So if you're just working in the upper, you could maximize this. You could have multiple programs loaded in here, but only one selected at a time. In the upper, if I were to select the program name, I can press the edit pin to the left of it, or under the program ribbon bar, press the edit button here. And this shows us the program in front of us. So if I were simulating, you would actually see the G code running in front of you, like you were standing in front of the control. But when making any G code edits, you simply put it into the edit mode, and it puts a yellow and black construction tape around it. You make any necessary edits that you want. When you're done, press the edit pin to save the changes and regenerate your program. And this will check it for any type of ambiguous code or anything that won't work in the program. Now in these examples, the program navigator is showing us 3 items underneath the program. You'll notice you have a little triangle that you can expand and retract, and this shows us the thought process behind how TurnMill is separating the operations in your program. So what is happening here? So if I were to select the % sign, you'll see that it will jump right to that point of the program. If I go to the N1, M1, T1, it jumps right to that point of the program, and M30 right to the end. So basically what's happening here is this is the beginning of the program, this is the operation or the beginning of the operation, and this is the end of the operation. So how is this happening? So in order to do this in the program, to separate your thought process and operations, you need to have a line number, M code, and comment. And you can see in my program here, I have line number 1, M1 optional stop, and comment, which would be tool 1 and a little description about the tool. So the benefit here is having the thought process separated here. You can easily drag and drop the operations around, whether it be from the upper to the lower or from the same path and reorganizing the paths. So keep this in mind, and this is how TurnMill can decide how the operation starts and how the next one starts as well. So if we had a tool number 2, it might start with N2, M1, tool 2, 80 degree. So how do we edit these operations? Now that TurnMill knows the operations, if you were to close the editor and you were to right click any one of these operations and say edit operation, this is what Complete TurnMill thinks is the operation for the beginning of the program. So all this code you see down here is just for the beginning of the program. If I wanted to edit this operation here, which was the cutting portion of it, I just select this operation, right click and say edit operation. Now it brings up everything to do with that tool. So we have N1, M1, tool 1, 80 degree, we have the tool change, and we have the generic tooling block. If I were to scroll down here, it ends at when the tool goes home. Now above this, it shows us which tool is being used and the G codes associated with the path. So it's trying to be smart here and understand what you're trying to do. So if we wanted to change this operation to work instead of the main to the sub spindle, it's very easy to do. All you do is change the spindle to sub. It will reverse the tool on the turret. It will change the TLO reference to now face the opposite direction. It will change the spindle commands to be from main to sub now, and the only other thing we need to do is mirror the Z-axis and reverse the arcs. It will automatically change which datum is being used as well. So when we press OK, it wants to know if you want to apply this update. We say yes. If we were to just regenerate just the upper here, so I'll shut off the lower and just make sure the upper's on, reset and start. Now my simulation is for just the sub spindle. So I very easily change this from main to sub, and I can change it back if I would like to. Press stop, rewind, right click this operation and say edit operation. We'll make this back to the main, reverse the arcs and mirror the Z-axis, so now it's facing the main spindle, and say OK. Apply the updates, generate, reset, and start. Simulation, and we can confirm that the tool path is facing the main spindle. Now you want to pay close attention to your simulation status that you see on the bottom right hand corner here, and this is your visual display of any warnings, or if you have all green and ready to go and can export your data. And you can see on the top here my status, I do have 2 warnings. When I bring this down, it says simulation checking is off, and that is because we have not collision checked this yet. Or I can click this and it shows me my collisions are off. So even if you were to regenerate this program with your feed rate overrides down or changed, and you were to look at the simulation status display, now you can see we have additional warnings. It shows that I have overrides on and I have no errors encountered here, but I can see that there's a warning here basically that the feed rate override is not at 100% and our rapid override is not at 100%. So I'm going to go back and reset this, turn this back to 100%, and the last thing I'm going to do is regenerate both of them, but this time I'm going to turn on my collision checking. And when we start this, it's going to create a swept surface around the objects that spin, and you'll see this in the 3D graphics window as it generates this. If there are any collisions, it's going to stop and report these back to you. When this is complete, when we look at the status simulation, we have all green here. And when you simulate your program in real time, those witness geometry for the spinning will show up. Now we're ready to export the programs. So to export the programs, we can just stop the simulation. On the program ribbon bar, just select program, export. Choose your programs you want to export and select your location. Just use my Turnmill series folder and say select. I'll make sure I have Open File Explorer after export. When we export them, you have your G codes that were modified or collision checked, ready to go back into your machine. For the next part of this e-learning lesson, this will be focused around our 3-path control series for the turret, and you can navigate back to our e-learning introductory for Turnmill. Scroll down from the top, and in our programs and reference charts by series, you'll note the first 2 being our SC and AS, which are our single path controls, WT and WY, which are our 2-path control series turret, and then last being our NTY3 series for our turret. We'll download the 2 files in here just by selecting the program reference and our programs here. And once these are done downloading, we'll extract this to our training file folder and review these 2 files. Now let's talk a little bit more in depth about this 3-path control NTY3 series. Now in the NTY3 series program folder, you will find 3 programs with P-1, P-2, and P-3. Now these are the path numbers respectively. If you label the programs correctly, they will import into terminal into the correct path. Now if we look at path number 1 program, which is the upper left path, it is a single tool program that works on the main spindle. Path number 2 is a program for the upper right, which works on the sub-spindle. Single path, single tool, single path program as well. Now path number 3, which is our lower path, can work on either the main or sub. So when we work in this, it's going to have tool number 1 facing the main and tool number 2 facing the sub. Now when we look at the NTY3 reference document, we're going to talk about this a little bit more in depth. The 3D diagram helps explain the different path numbers, and you can use this if you're manually creating programs or need a reference to work in. Path number 1, upper left. Path number 2, upper right. Path number 3, working on main or sub. Now on the left hand side, we show the turning and milling codes associated with the main spindle, and those associated with the sub spindle on the right hand side. Now a little bit more information about this 3-turret series and the machine it was originally designed around, and probably will explain why the upper paths work a little bit differently than any other Nakamura. Now to help better explain the 3-path control NTY3 series, I've gone to Nakamura's homepage and brought up a machine called a TW series. Now this was Nakamura's first multitasking machine, and it actually did not multitask. It was the first machine that came out. It had multiple controls, and you actually pushed 2 cycle start buttons at a time, and it ran a control program on the upper left and a control program on the upper right. And the only multitasking that was ever needed was weight codes that would talk from one control to the other. And this is where multitasking began for Nakamura, and it has evolved into what we are learning about today. Now the logic that you see in this machine was basically a slug style machine, so you could run the same program in the left spindle and then the same program in the right spindle. So that would be the same Z direction into the part, and they would have the same spindle codes for controlling the spindle. Now when we get back to this 3-turret series, the upper left and the upper right in path 1 and path 2 work identical to this TW series machine. So it gets really confusing when you're learning about multitasking. So I have a completely different approach to these series machines, and I do not teach you to program them like we did the TW series that I show you on the Nakamura website. Now I prefer to use the codes you see here when controlling the sub spindle and the codes that you see here when controlling the main spindle. And the only difference between these programs is this upper path has a different Z-axis direction. I know this is confusing because the lower path would be one direction and one direction this way. So when you're working on the sub spindle, if you're slaving the lower right into the part, you would think it would be plus direction into the workpiece. Well, on the upper path 2, it's actually a negative, so it matches the path 1. So this is why the programs that we see and about to review have this direction that you see. Now the other thing in this program chart is a standard program format that you can use when working on this machine. This would be the upper path for left, showing us how to start the program, how to call the operation, how to end the operation and end the program. And with the lower as well, we see how to start the program, how to call the operation, end the operation, start the operation, and end the next operation, and end the program. Upper path right would be to start the program, start the operation, end the operation, and end the program. And now we're ready to begin the example for the 3-path series control. Just like our single path and 2-path controls, we start with the top project ribbon bar, select your machine, and you'll have a default column and a setup name with all the different configurations you have loaded in your resource manager. I'm going to choose my NTY3 150 and make it the default, so every time I start the software it's automatically selecting that one. So if your plan is to always use a certain configuration, you can set it as your default. Document units are very important. This is the actual document units of the programs and how you want to see the machine set up. Now, once you choose this, you cannot change it once you start a project. So keep this in mind and choose this correctly when you first start. This project is in millimeters, so we'll press select and load the machine. Now that the machine is loaded, we're ready to begin. Let's start off by loading some of our resources. No particular order. We're going to start off with our work holding. From the top project ribbon bar, we'll go to main or sub. Both bring you to the same area. We'll make sure we're on main spindle. By default, the tab is on chuck. We can also load a part in stock. Let's load our chuck first by pressing select. By default, none of the filtering is turned on, so if you want to load anything that wouldn't fit, you could, but we'll use the filters and it will automatically filter through work holding that fits on this spindle. I'll choose my 8-inch 3-jaw and say OK. Once this loads, I have the ability to load a chuck option, so we'll press select and it will automatically filter through our resources for components that fit on this chuck. So I have a set of jaws here that I'll select. And it will start building my setup here. You can see in my 3D window, it's slowly building up the setup. I'll go to my part. We can set an extension length, and this is in machine coordinates. So let's set this at 80 millimeters from the face. We'll press import and we'll navigate to our part file. And by default, you have 4 different types of files that we can import from IGES STL, the Vermal file that we're going to work with, and the complete CSI geometry file. So let's make sure our file handler is set to VRML file, and we'll select the sample 1 main, and this is created in millimeters. Press close, we'll take a look, and it's slowly starting to build our setup. Now we're going to load in the sub spindle. So we'll go back to where we were and just go back to sub, and we'll select our chuck, use our filters, and we'll select the 6-inch 3-jaw chuck and say OK. You can see it start to build it. We'll load our chuck options, and it has a couple different sets of jaws that we can work with. We're going to choose sample 1, say OK. And when we go to the part stick out length, this is in machine coordinates as in the bottom here. So this will be negative now. So negative 80 millimeters. Import. And by default, it remembers the last folder you were in when importing geometry, and it remembers the last file handler. So we'll select the sample 1 sub and say open. This was created in millimeters. And press close, and we look in and we can see it's starting to build the setup. Next, let's load some tools. So we'll go back to the top ribbon bar under Tools, and we have 3 different paths now, so it can get a little congested. So you have the ability to minimize these paths if you're just working in one path, or expand them. The left upper, we'll select tool number 1, and we'll load our turning tool block. By turning on filters, we can fit the holders that will fit on this turret. So we'll load a generic tool block, turn 80 millimeter, and say OK. To the right of this, we now can select our geometry. If I had a big enough screen here, you would see it building the setup. You can press select, and it shows me the available cutting tools that fit in this block, and I have one called a 80-degree 1-inch stick tool. Say OK. You can set your stick out length by using this adjust extension here, by manually setting it with the jog, or by using the auto adjust. If this was a boring bar, this would be a little bit easier if you're inside the part to set the stick out length, or you can specify the maximum stick out length on this cutting tool by just putting in a hard coded number. Now if you're in the document units, which we are in millimeters, when you type a number in, that's the units it's working in. You could put a value in here of completely different units by putting in, let's say, 2 inches. And you can see it's automatically converting it. Press close. Now you do have the ability to flip here, and it's not like this turret can actually handle this, but it still has this user interface in here. In the upper left, all tooling will be working on the main spindle, so this will not change. So by default, it will automatically associate all tools to the main TLO reference datum, but it still allows you to flip them if you had drawn the geometry backwards. So just some added flexibility there. We'll go right to the right upper, and the right upper is facing the sub spindle, and we'll go to tool number 1, and we'll load a OD turning tool. So we'll turn on our filters and load the turning tool block. Say OK. And just like we did in the upper left, we'll load a cutting tool. Same cutting tool appears, and we'll leave the stick out length at the default here. Next will be the bottom turret. And you can see on this machine the guard work is a little bit covering everything up, so I'm just going to close this and change my view here so I can look at an overview and see a building. Go back to my tooling page, and I'll go to the tool number 1 on the lower, and I'll load the same cutting tool, but I'll face it towards the main. So I'll load my turning tool block, select my cutting tool. I'm not going to set an extension length, I'll use a default. And by default, this is referencing the main turret. So if I were to look at it, it's facing that direction. I could flip it if I wanted to. This bottom path on this series does allow you to flip this tool and work on the main and sub, and it will change the TLO reference to reference the datum control on the main or the sub. On tool number 2, we're going to load the same exact tool here. OD turning tool, select the default cutting tool, but this time this is going to be flipped to the sub spindle, and it will automatically change this. And we'll take a look at the setup, and now we're ready to begin and move forward. Now we'll load our programs just by going up to the top ribbon bar, Programs, Import G-Code, and we'll navigate to our turn mill folder to the NTY3 folder, and we have our 3 programs there. By default, the file handler is set to the generic G-code files when you're importing G-code. So if you automatically have the correct extension on them like we do here, you could simply load them just by highlighting them all and saying open, and it will automatically populate them in the correct path. Now keep in mind, you could reload these same programs. So if I had more than one program in a path, so I'll just load program 01001P-1 and say open. It loads it into the left upper path, and only one program can be active at a time. So think of this as memory mode for that path. This being the directory, and this being the actual path called into memory. So this little red flag on the left-hand side allows you to select which path is active. Deleting any path is pretty simple. Just highlight it and press delete on your keyboard. And now we're ready to create the interpolated motion. Creating the interpolated motion is quite simple to do. On this 3 turret series, one thing to keep in mind is you can only generate it on a single path or all 3 paths together. You can't do 2 paths. You have to do all 3 or 1. Now the way this works is right below the programs that you loaded, there's a section called Simulation Status, Regeneration Required. So we select the path that you want to program. I choose the left upper path. And at the bottom you have your generate simulations options here with a start, stop, and reset. Now this is clear white right now, which means that there is no interpolation generated and there is no simulation available, so we have to create it. So what we do is just press start. And what happens in TurnMill is it checks your G-code for any ambiguous data. If you're running all 3 paths at the same time, it will look for any type of weight code mismatch as well. Once you're ready to simulate, just go to Simulate, and we have our simulation controls here, or in the 3D window, or we have what's called the slide navigator here, which works like any type of movie player. Since we have all the different simulation steps, we can do this. Or you just use your real-time simulation, press rewind and play. Now if there's interpolated motion already generated, you can reset it fairly simple. Anytime you make any type of adjustment in here or change any of the resources, whether it be the work holding, tooling, or tool offsets, or G-code edits, you need to regenerate the interpolated motion so that it can properly account for the time change that is in place. Now on this I've generated the interpolated motion on just the left upper, but this time I'm going to reset this and generate it for all three paths and say start. It's created a successful string here, so I can simulate this by pressing play, and now it's showing all three paths running at the same time. Now depending on which spindle you're working on, you can go up to the simulation and go main, and your focal point is on the main spindle, or you can press sub spindle and it focuses on the sub spindle. So in this program, the upper right is waiting for the lower. Editing the G-code is fairly simple. Just select the program you want to edit, and on the left hand side you can press the edit pin, this little A here, or go up to the top ribbon bar to programs and to edit. Once in the edit mode, if you had multiple screens it might be easier. You can put it into construction mode by putting the enable editing mode on, and it will put this yellow and black construction tape around the program, which is the editing mode. You could type in anything you want, and when you're complete you can shut off the enable editing and it saves the program, and it requires you to regenerate the interpolated motion again because you made a change to one of the settings in the project. So we just got to go back to generate, reset the interpolated motion, and recreate it. When you create any interpolated motion, you want to pay attention to the simulation status bar. Under simulate on the right hand side we have a status bar, and it also shows us any warnings up the top here if we expand this. By clicking the simulation status bar, it will show us a visual status, and this is really the only visual status we have when working in the project to show us if we are all green or if there's any warnings that we should be concerned with. And for this project we haven't done any collision checking. So keep in mind if you have any type of changes to the project. So I'm just going to go back to this and to generate and reset this and change my G0 and my G1 feed rate override and restart this. When I go back to the simulation status here, you'll notice that I have some different warnings here. And now it says that the feed rate override has been changed, and someone changed this by default, so the actual timing you see here is different. It's just like being in front of the machine and turning up the overrides or turning them down. So I'm going to go back and reset this. And the last thing we're going to do here is collision checking. So we just, on the generate screen, we turn on the collision checking, and we can reset and start this. And the way this works is it's going to create a swept surface around any objects that spin, and you can see it's created one on the main and sub, and these are the collision checking entities. And if there are any collisions, they will be reported to you, and you can correct them at this time. And once it's completed, it's past our collision checking, we can simulate the program now. And when you do any simulation, you will see a witness of this swept surface that it's using for collision checking. If you zoom in closely, if you have any 3D geometry, it's created that around the part as well. Once your project is complete, you can export the G-code just by going up to the top ribbon bar, Programs, Export. You can select which program you want to export. On this 3-path, we return on all 3. Select our directory, and I turn on Open File Explorer after we export it. If it sees any programs, it will ask to overwrite. And your 3 programs are here to import into the machine.